Hello everyone, August the 7th. Alright, let's get on to it. Longest increasing subsequence. Given an integer array, return the length of the longest. Oh, I gotta have the solution here. How do I cancel it? Alright, there we go. Return the length of the longest strictly increasing subsequence. Subsequence is a sequence that can be derived. We know what subsequence is. So that's for 2, 3, 7, whatever. O and log n time complexity. Okay. Longest increasing subsequence. We want the length. Alright. Are you telling me that this can be done with O(n) squared? When the longest, we can say, if we do dp with the longest ending at a certain position, and the next one we want to find the longest ending at a certain position. So I need to find something that's smaller than 3, right? Like if it's 10, that's longest that we want. 9, we need to find the longest that's smaller. The larger number that's smaller than 9 is in the front. And then that's O(n) squared. So every time, like a 2, I'll loop through the previous, we find a 1. We don't have, so that's just 1. And as 5, we need to find something that's smaller, so we find 2, right? And if it's 3, we need to find 2 as well. If it's 7, we find 5, which is 2, so this will be 3. And this one we find this, which is 4. And this one we find this, which is 4. So this one is 4. So we can do this O(n) squared. Let's just code O(n) squared without issue. Right? O(n) squared shouldn't be an issue. But O(n) log n, that don't have a clear idea immediately, but we're gonna see. Alright, so we can have dp is equal to n equal to ln nums 1 times n, right? And then we say for in enumerate nums, right? For each I, we're going to say for j in range all the way to I, and we need to find the one that's, I just loop through and find something smaller than this. Yeah, we can do that. We just need to find the largest. We're going to say if nums j is smaller, cannot be equal to nums I, then dpi equal to maximum dpi and nums, not nums, dpj plus 1. And blah blah blah, we're going to return dp, actually maximum, because we want to find, let's just maximum dp. Okay, let's try this. I mean, it's 2,500, so not worried about the time. Time shall work no matter what. Length. Yeah, I don't worry about the time complexity. I think the time complexity will work. It's just gonna be long. Oh, are we timing out on this or are we error on this? Yeah, we shall be fine because only 2,500. So it's not too big a deal. Right. But is this optimal? Definitely not optimal. So O(n) squared. Naive BP solution. Yeah, it definitely increases the number of test cases. Okay, so now let's think about how to make it faster. O(n) log n. I mean, what we want is just to find, and we cannot binary search it because it's divide and conquer. Not really. I mean, 10 to the fourth. 10 to the fourth. What are you thinking about? I'm thinking about fill out an array of length 10 to the fourth. And we just fill the number in. Well, if we have encounter, we just set it to 0. If we have encounter, we set it to 1, or set it to whatever it needs to be. But no, that's not working. Huh, interesting. How do we handle binary search in this? Are you saying that because it's so short, we can always sort every time? That seems to be very weak. That seems to be very weak reasoning. And I won't count that as O(n) log n. But it's definitely going to be faster because we only have 2,500. So if we sort, it literally, I think it might work. Sort is O(n) log n, but this is O(n), right? This is actually faster than sorting. And how do we keep it in order? Interesting. No idea. Oh, solve it 4 times. I still don't know what is the best way. Yeah, that's quite embarrassing though. Still no idea. The first idea is always the longest. Let's see if we can get some hint. What is this? An auxiliary list. Swap. Oh, this is an interesting idea. Smallest value in nums, that is the end of any length of LIS. That's true. The current value is going to be located. The current value is the largest we append. Otherwise, we find where it's supposed to be, and then we swap it out. Oh, I see. That's the idea. Yeah, I'll never be able to figure it out. Did I use a BIT for this? I think I got this idea last time, because I think this is, I got it the last time. Yeah, didn't get it this time. Okay. Yeah, the ability definitely dropped. Was able to do this much more easily in the past. So the binary search, the idea is we want to find the longest, right? So, but we cannot. So we need to do binary search, which means we need a sorted array. But we cannot do the sorted array right now. But what we can do is we can build, right? We can build it. So what we can do is, as we move along, right? As we move along, we can build an auxiliary array. But hold on, you cannot change position, right? No, you cannot change position. Then I say I find a 10, 9. I say I can replace this because it's a smaller. Okay. And then as 5 we go, have 2, 5, 3. I say I have 3, I can replace 5. And a 7, 101, and an 18 replace. So which means as we build, if it's something bigger, then we apparently append to it. If it's something that's can replace something in the front, are you saying you're going to replace it? Yes, we are saying we can replace it because it's fine, right? All we want is just a sequence. And the reason we can replace it because if we replace it, it doesn't change the position of everything else. Everything else stays the same. So not like if I replace some value to a smaller value, then we're going to change everybody's. It's just, it's just to keep it sorted, right? We keep it sorted and then make sure that everything is positioned correctly. Yeah, like we can have 0, 1, 0 again, and then 3 we append, but 2, like, okay, 2 actually I can swap 3, because if we swap 3 with 2, it gives us more chance. So we swap 3, and then we have 3 again. Right? And if we have, so let's say we have a 1 here, right? We can have like 2, 5, 2, 3, 7, 101, 18, that's fine, but we can have 1. We put 1 in front, it's not going to change anything, right? But we need this logic, like especially for the last one, we want to update, right? We want to update, and we actually want to update everyone, right? And yeah, I think the key is just when you update something, when you update a value, it doesn't change the fact that a subsequence exists to fit this pattern. But what it does change is it provides more opportunity to get more in because we are swapping a value to a smaller possibility. Yeah, so that is the key. Yeah. Not 4, 1. To accept. Create. Okay. I call it auxiliary. Actually, I don't like to call it DP. And we can do nums 0. That's fine. Okay. I in range non-nums. No. Index. Bisect right. Right, we say if index is equal to len auxiliary, then auxiliary dot append nums I, else auxiliary index. What if index is 0? If auxiliary is 0, then we shouldn't do -1. Now we should never do -1, right? Because it's insert after this, even if it's the same. Oh, if it's the same, we shall the aleph index and auxiliary index -1 is Now let's do this. If aleph not this, or no, aleph index, aleph not index, or not index, or auxiliary index -1 is not equal to nums I, right? Then we can just do this equal to nums I. I'm just saying that due to auxiliary is going to auxiliary index is the slightly bigger version, right? So we just replace it, unless it's the same value, right? So this just means it's the same value. Then we're gonna return lines of auxiliary. Yeah, we can try this. Oh, hold on. The heck? Oh, I have to do this first. Shoot. Huh? You know what? We have to skip. All right. If index and args index minus 1 is equal to nums I, then we have to continue. Then we say if else args index equals nums I, something like that. Yeah, it's much faster. Auxiliary, that's where the binary search comes from. Okay, all right. Let's do this. So we have a good solution. We have a dummy solution. So we are going to build tests. So we're going to say solution 0, right? Specifically pointing to the solution 0. And the solution is equal to solution. And the tests, we're not going to be bothered with these tests. I'm going to say num tests. Let's do 10 tests. Len, what is it called? Len nums. Len, that's called L. So 10. Max, let's do 10. And tests shall equal to, for this in range num tests, right? And then each test contains something, right? For this in range L, and each one is going to be a rand int from 1. I believe it's from 1. Yeah, 1 to max. Wow. So this is our test. Then we can say for blah blah blah, but there's no answer. All we have is just the tests, right? And answer equal to solution 0 dot total steps nums. If it's the same, actually if it's the same, we don't have to do anything because I don't want to print out tons of stuff. Just if it's not the same, print it. We can say test is gonna be tests I, answer, and this. Answer is not defined. Oh, my bad. Okay, so yeah, so this is good. Therefore, we have to increase it to 100. All right, so now we have a failed test case. Let's see what happened here. So we have, you know what? In this case, we can probably get it down to 5. All right, let's do more tests. Number of tests. Oh, 5 doesn't cut it. No, it doesn't cut it. How about 6? Okay, 7. 7 we have. All right, let's pick the first one. 85, 57. Maybe we can go smaller. I'm not a big fan of large values. There we go. This is the one I like. 20, 10, 16, 2, 8, 8, 16. Answer is 4. So the first step. First step. Okay. The second step. This is bringing together. And third step. And fourth step. Yeah, we need 4 steps. Alright, so in my current solution, this whole gibberish stuff. So we have 20, 10, 16, drop down to 2, 8, 8, 16, right? So we say first drop 10, that's one step. 16, so 10 we have the previous pointer 20, and then we have a situation of nums j is larger than, right? And then we say the pre-peak we find as 20, and auxiliary.append something, which is we're going to append 2. Nums is larger than, no, it's not larger than, so this shall be 2. So 16 shall be removed 2, right? 16 shall be removed in the second step, which is correct. And the previous peak is going to be 20. So 16's previous peak is 20. You know what? We need to comment out this and create this. Actually, not this. Let's do tests equal to. So what do we have here? We have this thing. All right. So what we can do is we will print auxiliary every single step. So auxiliary, this is 0, 0. This is 0, 1. Previous peak, and this is 0, 2, which is understandable. And then for 2, we drop down. So we shall reset. That shows 0, 1, 2. I'll say it's 2, 1. Right? So that's the first step. And then that should be 2, 2. Exactly. Now they're equal. Oh, that's probably the problem. They're equal. Then we say shall be 2. Then which step it shall have? It's step 3. Exactly. That's the third step. Because I will delete this, right? And then delete this. And then finally, the last one is 16, which is equal to what we have previously. And in my current logic, I think it'll be 0, 3. That's why it's going to 3. But the 16 is deleted in the second step. So first step is clear. Second step, we'll delete 16. We'll delete 8. Well, actually 16 and 8 is deleted in one step. Oh, they're deleted in one step. You consider that. They're deleted in one step. And then this one's deleted in the third step. 8 is deleted in the third step. The logic is not right. Because there's something inside. So 16 has to be deleted after 8 is deleted. So shall be the maximum of the two. So you're saying every time increase, I check the previous, I check that, shall be the maximum between the two. Which means if I set initials this, okay, and then if I am larger than the previous peak, then if the previous one is 0, then 0 else shall be the maximum of aux minus 1, 1, and this maximum, right? And then if we're equal, then it's this. That will break. Else pre-peak index, okay? once I come out, we say if it's not set yet, then if equal, yeah, that's fine. Still, I will say I'll get the maximum out. And this one will pass. So basically the thing is, as we go, if it's not taller, then definitely we just +1, right? But if it is higher, so we always, yeah, that's the baseline, it's going to be +1, right? But we just, every time we have to find a maximum. Okay, so I'll come out this, obtain this. Oopsie doozy, don't want to do this. All right, so let's do 100, length starts to 10. Okay, about 1000, 100 with this. All right, this looks promising. This actually looks very promising. We are going to throw, this is the holy grail. This is the holy grail, man. This is what we fail to pass for so many times. Okay, this one shall fail. But where it fails, this one shall rule. Come on. Try it. I think this one will rule. Go for it. Come on, show me some love. Got it. We got it. But look at this complicated logic. I can't even describe. Let's see if we can make it even simpler. This is ridiculous, to be honest with you. Gotta be a faster way than this. Okay, I need to regroup my thoughts. So we did solve it by ourselves, but Lordy, when was our first attempt? That's actually not the first attempt. I think that's like maybe the second day of trying this. Maybe on the third, so almost for 5 days. Okay, so the idea is we have an auxiliary array. Auxiliary array again. Yeah, sometimes you just have to think. It is not a DP array. It is a DP array, but it has some more functionality than that. So what we do is we will, for each value in nums, right, we will find its auxiliary, which is index of previous peak, larger than me. It's the immediate previous peak. And number of steps that needed to remove me. That's the two things. So as we go, we know if we keep increasing from the start, right? So increasing, none of those will be removed. They're all good. So that's basically what we're doing, right? So we set up, that's the first value. We'll never remove the first value. And from the second value, we're trying to find the first peak, basically, right? So we say, if I is larger or equal to, that's a non-decreasing than the previous one, we just keep going. And every time, I am my own peak, right? And then once we drop for the first time, that's when we get out. And of course, we have also this little case, which means if it keeps increasing, then we don't do anything. And then we count the current one, which you just pushed in, and it has its peak, which is the previous one, and we'll take one step, right? One step to remove me. And then we enter this convoluted logic, which we start from the next one, right? And then we say we have, basically, I laid out 4 different situations. So the first situation, you know what? Why don't we just write it down? Come on, man. Don't just keep talking. Write it down. All right, so this is a very, very convoluted. This is a very convoluted logic. First, we use an auxiliary array to store each values, to store 2 pieces, right? 2 pieces of information about each value. First, the first peak to the left of the value that is larger than it. Now the index of the first peak to the left that is larger than it. Second, the number of steps needed to remove the value. We store these 2 values as a list of length 2 and always appended it in a 2 auxiliary array. That's the first step. Second, start from the beginning, right? The beginning of nums. No, that's not the spelling. Begin, ing. And look for the first peak. We know that all the values leading up to the peak, including the peak, will not be removed. All the non-removed values will have their auxiliary entry being I0, right, which means they are their own largest peak to the left, and it takes 0 step to remove them. The first value, the first time that value drops, we recorded it in aux as I-1, 1, which means the first peak to its left that is larger than it has index I-1, and it takes 1 step, right, to remove the value. Now, the real logic. Now the more complex logic kicks in. Right. Iterate through the remainder of the array and consider each of the 4 scenarios below. A. A downtrend. Right? A downtrend. Say nums j smaller than nums j-1, smaller nums j-2. So a downtrend continuous, right? Continuous downtrend. This means, right? This means nums j will be removed in the same step as nums j minus 1. Thus, it has the same auxiliary entry as auxiliary j minus 1. B, what is B? Nums j smaller than nums j minus 1, okay? But nums j minus 1 is larger or equal to nums j minus 2. So nums j minus 1 is a peak or extending a peak. In this case, nums j minus 1 is the first peak to the left of nums j that is larger than it. Hence, auxiliary minus 1 shall equal to minus 1, 0 shall equal to j minus 1. Right. And since nums j minus 1 is a peak, our step count must reset to 1. Hence, auxiliary minus 1, 1 is equal to 1. Okay, that's also good. These two are simple logic. So the third one is nums j is equal to nums j minus 1. Right. So we are extending. We are extending whatever happens before. Apparently, nums j and nums j minus 1 has the same peak to the left that is larger than it. So auxiliary 0 shall equal to auxiliary j minus 1, 0. And it is always the case that actually this is a little bit more careful with that. With regards to the number of steps, it depends on whether nums j minus 1 gets removed, right? If it is not removed, then neither will nums j. However, if it is removed, then nums j must be removed after nums j minus 1. Right. Hence, auxiliary minus 1 shall equal to 0 if auxiliary j minus 1 is equal to 0. Else, auxiliary j minus 1 plus 1. Okay, that's still easy logic. So now this is the most complicated one. Nums j is larger than nums j minus 1. So this is the most complex logic. Now, the current value is bigger than the previous. We have two scenarios. One, the easy one, or one, the trivial one, is that nums j is smaller than, right? Is smaller than nums j minus 1. Than the previous peak, of this. And nums j will have the same previous peak as nums j minus 1, and its step count will be the step count of nums j minus 1 plus 1. However, if nums j is larger than the previous peak of nums j minus 1, then we must keep searching, right, for the previous peak, right, for the previous peak of the previous peak of nums j minus 1. And we must keep like this search until we either find a previous peak that is larger than nums j minus 1, nums j, or we end up with a previous peak that is the previous, that is not removable. If it's the latter situation, that means nums j is also not removable. If it's the former situation, we have located the previous peak. With regards to the number of steps, each time we progress towards a new peak, right? The new previous peak, the current peak, the current value we compare to has the potential to be the exact value that is removed right before nums j. Thus, we need to record and to update nums j, the count, the step count of nums j with the step count of each value compared to, and keep track of the max steps along the way. Actually, we can just say this can be simplified. All right. Now this must equal to auxiliary previous peak index 0, so they all have the same previous peak, and auxiliary minus 1 shall equal to auxiliary previous 0 if 0 pre this 1 is equal to 0, else that would define maximum. So we can remove this. Yep. Yeah, that's the steps. Runtime, I think, is ON because as we go through, these are all ON, and these are all, the only thing is just going back, but this one, actually, how through sure it's ON? And we're jumping back, but actually, I don't know. Maybe amortized is ON. Actually, I don't know. Runtime, not sure. And this must not be the standard solution. Alright, so now it's time to check the standard solution. Stack DP. Wait, there are hints? Oh, I didn't even check the hints. Okay, maybe we can figure out the solution by the hint. We are doing that. This is exactly what it is. DP previous plus 1 and DP removed index. Okay. Maximum, the number of rounds it takes to remove. That's a monotonic stack. So you're saying this is essentially a monotonic stack, but without removing anything. So we can build a stack, right? And we can push 5. And we push 3, then we can pop 5, so we have 3. But every time we pop something, actually no, we don't pop 3. 3, we keep 3. But when we keep 3, we should push in the previous peak, so we don't need the information of previous peak, because previous peak can be found by popping if it's a monotonic stack. Okay, I get that point. So every time we push, just push the number of steps in these, so that would be 0. And this is smaller than previous, so that would be 1. And this, if it's smaller than the previous one, that will just be equal to previous one, right? Huh. Okay. And then 4. That is the same. So if it's smaller and if something larger comes in, right? If you're smaller, we just pop you. And when we pop, we will find the maximum. Yes. And then we keep popping the maximum of this plus 1. No, I think it's DP removed index plus 1 and DPI. Oh, we just keep popping. Then we need 2 arrays, right? One to record the number of steps, and the other is just indices. Okay. And of course, after we finally stop, right? After we finally stop, we will look into this. Oh man, hold on. Finally stop. And 5, and 2 plus 3. But 4 is bigger, so 4 pops 3. But we stop at 5. Okay. Now 4 again. Don't pop. So now currently we have 2. Right? 4 coming in, we don't pop. In those situations, what value should we give it? Plus 1? Interesting question. So 4 push in is the same, right? If it's smaller, No, I don't. Let's read. What the heck? What the heck is this? Honestly, people, comment. Alright, that was happening in May. Let's just read the code to see if we can understand what it's trying to do. So we have a DP, we have a stack. Yeah, this probably fits my current understanding better. So we iterate through, right? Stack and A, which is current value, is larger or equal to the end of the stack. Okay, then we shall pop it, which is fine, we pop it. And we go to DP to look for the number of steps it takes for that to get. So we basically pop everything, and each time we pop, we get a maximum, we get a maximum, we get a maximum. And then we say if stack, which means if it's not stack, because if I am larger than, then we all pop the stack. And if it's not stack, then I am the largest. So I don't, then there'll be 0. Yes. But if there's something in there, that means I will be popped. Then what's the number of steps I need to be popped? It is the current plus 1. Current plus 1. Basically, what it's saying is if you have anything that's smaller than previous, that's exactly as what we do in here, but we just make it a lot more complicated, right? We're doing this maximum thing as well. So if something is smaller than you and you pop and then you say I will definitely be removed after something in front of me that's smaller than me, right? And in this process, we have to keep looking forward. Like here, what I just used this like a pointer pointing the previous peak. But what we can do, we can just pop, 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 pop until we cannot pop anymore. And that will be a previous thing that's smaller than me. Then everything in between, right? Everything in between the smaller than me and me, everything in between us are smaller than that thing. So they will all be popped. But the number of steps, I just need to find the maximum number of steps because before they all get popped, right? I will not get popped because if it's I'm larger pop, I'm smaller than the previous one. Right? So before they will before I can get popped, they must all get popped. So I need to pop all of them to find the largest step. That will be me, right? Okay, I understand that. That makes sense. So for each one, if I am smaller than the previous one, right? What if I'm smaller than the previous one? If I am smaller than the previous one, then what do I do? If I am smaller than the end of the stack, then DPI doesn't change. It does not change. What the hell? Oh. Yeah, we'll append I, yeah. But that will point to 0, which is correct, the first one. What about the second one? The second one was smaller. A is larger equal to, no, A is not larger equal to, A is smaller. Say if stack, yes. Oh, current plus 1. I see. Oh, that makes perfect sense. That makes perfect sense. Which means every time when we start considering, it's always 0, right? Yes, it's always 0 steps. And then we try to see, okay, do we have anything to pop? Like, is there anything in between me and the previous peak? Yes, me between previous peak. If there's nothing between me and previous peak, then it will always become, it actually always 1, which makes sense because if you are on the downtrend, no matter where you are, if you're on a downtrend, you're always the first step. It's when you go up. That's the difficult part. Oh, damn. That was so good. So good. Alright, we need to record this solution. Anyway, after this, it's actually a little clearer. His solution, like my solution is quite close, despite being a lot more verbose. But his solution helps me understand the problem better. So, what is clear is that the difficult part is always having a value, right? Having a value larger than some previous values. So we to figure out what to do with such value, we must find a previous peak, right? A previous peak that is larger than the current value. In my solution, I use some pointers, right, to keep track of each value's previous peak. but this can be more easily achieved via monotonic stack. In particular, monotonic decreasing stack. Given nums I, right, and a monotonic decreasing stack, as long as nums I is larger or equal to the end of the stack, we can be sure that nums I must be popped after the end of the stack. Thus, we keep popping the stack and keeping track of the largest number of steps needed to remove any of the popped value. We stop until the end of the stack is larger than the current value. This means the current value must be removed after all the values in between. Let's say then until the end of between stack -1, right? And nums I have been removed. Since we have kept track of the max number of steps needed to remove all the values that have just been popped, we know that to remove nums I, we must use max steps plus 1 step. Now the beauty of this approach is also that if we pop everything in the stack, then nums I must be the largest value so far, which means it can never be popped. On the other hand, if nums I is smaller, is immediately smaller than stack -1 without any popping, then we know nums I must be removed in the first step. Because without popping, nums I and a stack -1 are adjacent. This is all when sure. Okay, so we have a steps and then we have a stack. Let's say for I in a create nums current step 0 while n is larger or equal to stack, while stack and equal to nums stack -1. Current step shall equal to maximum current steps and steps stack dot pop. Right? It's the index pop out. So we'll keep doing this. When we're done, we say if we have a stack. Right. If we have stack, then that means nums, that means n must be removed. Then we say steps I shall equal to current steps plus 1. Else, otherwise n will not be removed. So there's no steps for that. And now we return the maximum of steps. Solution 2. Oh, the heck. Oh. The append I. Yeah. Marvelous. Okay. Alright, that'll be it for today. 1 hour, 25 minutes. Yeah, it's not too bad. And not too good either. But we did solve it ourselves using this convoluted logic. Yeah, when you think about it, you have to remove it. I have to remove everything in between. Once you start thinking that way, it makes more sense. Okay. I will see you guys tomorrow. Adios.